So now let me introduce the first speaker, Dr. Mike Hahn. Dr. Hahn directs the neuromechanics laboratory in the Department of Human Physiology and also teaches the Bowerman Sports Science Clinic at the University of Oregon. He teaches courses in biomechanics and technology development. He also researches the neuromotor adaptation, which relates to the design and the application of assistive devices in sports. So please welcome Dr. Mike Hahn and his talk, Biomechanics and Physiology, Tools of the Trade.
Thank you very much for the kind introduction. I have a bit of a cold that I'm catching up from, I hope, and so occasionally I may need to cough, which I'll try to dampen with removing the microphone. So it's a nice drive up from Eugene to this place called Hillsborough, which is a long way west of the interstate. I've never been this far west of I-5 except to go to the coast, and so it was intriguing to come out and see such a great thing that the University of Oregon would be jealous to have, actually. This is a fantastic setting. So I wear two hats at the university. One of them is to conduct my research in neuromechanics, which we work with a lot of power devices like robotic prosthetics and exoskeleton systems a bit. And that I thought might be a good thing to talk to you about, but I also thought maybe that's too close to where you are, and you might need expanded into a different terrain. So the other great thing that we get to do at Oregon is, University of Oregon, is work with a lot of athletes, specifically those who run around this oval-shaped thing here called Hayward Field. And so my laboratory is based in the Bowerman building. I don't know if the pointer is working very well. So this is on the northwest corner of the track, and in that we do our mechanics work as well as our work with athletes. So some of you may know we have just about every 4 years some Olympic trials for track and field are hosted here very often. And so my lab again is in this bottom left corner, and it gets consumed by all of the officials and media and athletes, and I get kicked out and have to take 2 weeks of forced vacation. So, but it's a good problem to have. So what I'll talk about today is some of the sport application for what our biomechanics and physiology work is, and specifically list off a few things about how we currently capture data and how we measure things for physiological performance, and then also what I think might be some opportunities for improvement and development for all of you as you go into university and learn some of these things a bit further and can improve everything and make it archaic what we're doing today. Some of the current services we offer in this thing called the Bowerman Sports Science Clinic are performance physiology assessments on post-collegiate pre-Olympic athletes. So the top two left and center are members of the Oregon Track Club Elite program, which often makes the Olympic squad. That's Ben Blankenship in the top center there. We also do mechanics analyses where we measure the motion of the limbs as people run and then quantify them essentially as a series of sticks and pin joints and quantify how much force or how much torque is passing through or about the joints and calculate the power needed to actually do those tasks. We also conduct body composition assessments. So this is a dual X-ray absorption system on the bottom left. It's fairly rough compared to a lot of the imaging that's out there. It's very low dose radiation. And with this we can get bone mineral density as well as assessments of fat and muscle distribution. So some of the cases we've been fortunate to work with are people who are trying to make the national team. And so we go everywhere from the race walker in the top right to Aisha Pratt, who was running for the Jamaican squad for a while in the bottom right, to high schoolers from Eastern Oregon who come to us for mechanical assessments. So it's quite a diverse group that we get to work with. Some of the interactions we have with clinic are with physical therapists who are able to come in and work with the athletes that we bring into the clinic as well. And we do everything from just basic PT assessments to technique about muscle control and how to maintain your alignment so that you're less likely to be injured. We can also measure force output by the joints. And when we measure this, what we have to do is kind of take out the real-world situation of running out on the track and take them into the controlled environment of the laboratory And so we lock them into these devices and then ask them to push against this pad. And if any of you have been into a physical therapy clinic, either your parents or yourself, you know that often physical therapists are a bit of torture devices themselves in human form. And so we use machines to torture our folks instead. But in this case, it's usually we're asking them to beat the machine, but the machine will never lose. So we always try to give the maximal effort. We use motion capture to get our mechanics analyses for the running assessments. So this is the same technology that's used for development of video games, EA Sports, anything that's an animation that represents human motion or even animal motion is coming from this technology. We use it just to create very simplified skeletal structures to assess how the human is actually running. And then we use that to, again, quantify how much actual mechanical work is being put through the joints to make the running event occur. And specifically, we're looking for asymmetries. So if I go for a run this afternoon, I may start out fine, but by the end of it, I may have some asymmetries that begin to show themselves in how my joints move. And if I continue to run, I'm basically transferring load from one limb to the other, and this could become injurious. And in fact, a lot of times we find that there are problems in the musculature pre-injury that could be detected, and these reveal themselves when you become fatigued. So this is why we're looking at both the strength, motion capacity, and then what their training capacity is as well. So some of the other tools we use instrumented treadmills that are force strain gauges built into them. And so these are devices that you have a full treadmill that is housed on 4 individual strain gauges. And so everything I do on that treadmill is recorded in 3 dimensions, as well as how much torque is applied about the treadmill axes as well. And so with that, we can break down basically everything about how the person is interacting with the ground. In this case, the treadmill is rolling underneath them, and then calculates back up from the foot all the way to the pelvis what the mechanics of the system actually is. One of our undergrads actually snuck in one day while we were building the treadmill and getting it installed, and apparently it was in the fall when everybody had zucchini coming out of their gardens, and he brought the zucchini in and decorated it, put it on our treadmill. So you can see that everything at the University of Oregon has to do with the ducks, of course, but the zucchini was a perfect color. It was green, yellow, and he just decorated it further to put it on the treadmill. Sometimes the resolution that we get from the force treadmills, as well as the motion capture, is a bit clunky. So you have an entire structure moving around, and we're minimizing it down to a stick and a force vector coming up through the foot, and we calculate everything in almost 2D planar physics, essentially. But clinically, we want more information than that. So we put in pressure insoles into the shoes and have them go and do their runs as well. And this allows us to get a very, or more precise distribution of where the force is actually transferring through into the foot. So rather than treating the foot as just some clunky triangular segment, we can now have a higher resolution of force transmission into that structure. And a lot of times we see unique aspects about how people run that can give us some idea about why they're becoming injured. So that was quickly biomechanics. There's a lot more to it than that. You're welcome to come take my class if you like. It's 3rd year human physiology course, or you can study a lot of this online as well. The other thing we do is performance physiology, which has to do primarily with cardiorespiratory function. So how much energy can you pump to your muscles in the form of oxygen, and then how much do you consume of that oxygen to perform these events. And so we can calculate a lot about how economical you move and how your mechanical efficiency changes that. So one of the most obscure track and field events is the 20-kilometer race walk, where you're not allowed to run, but you're supposed to walk as fast as possible in order to compete in this event. And it's 20 kilometers, which is, anybody run that far before? This is about as much as like 2 full Barclays Premier League matches with the elite footballers. So in this case, they're doing it around the track the whole time. So I don't know how they can do this and not go crazy. But they end up with a very, very unique mechanics profile. And what's more important to us then is to study how can they efficiently do this and economically deliver the energy with their cardiorespiratory system. So can their heart pump the oxygen-laden blood efficiently enough to then allow their muscles to use that energy? And can we return and get the kind of byproducts out of the system fast enough to allow people to perform for 20 kilometers? So this is about the only data that I will show from the talk today. On the x-axis is heart rate, on the left x-axis. On the right is what we call blood lactate. This is a lactate ion that we can detect from the blood. It's one of the metabolic byproducts of energy use. And along the bottom on the x-axis is the speed in kilometers per hour. So with this individual, she was walking in February across this variety of speeds, and we recorded the open circles as blood lactate and the closed circles as heart rate, and recorded across those speeds what her performance was. 5 months later, after we gave her some training feedback based on how she was able to perform these things, she was able to move these two lines you see vertically, and her performance to about 0.5 kilometer per hour faster to perform the same tasks for this, which may not seem like much, 0.5 kilometer per hour, but for a race walker, this is the difference of being on the podium or being 10th, perhaps. So in this case, she made the national team after using our feedback, which was quite fun. Because we take these classes and we teach these classes, and we know the physics, we know the chemistry, we know the biology, we know the anatomy, and we say it should work, the textbooks are right, and we teach what we think is right, but when you actually see an athlete demonstrate this in principle, it's really fun, because our students don't really know whether they should trust us or not, but when you can show data like this, they say, it works, this is real, this is good. So typically in a given year, we work closely with the middle distance runners from the Oregon Track Club Elite. They're the 800 and 1500 meter specialists, sometimes up to 5 kilometer specialists. And we work with them in the fall to kind of lift up the hood and see how the motor is, essentially. So kick the tires a little bit, put them through their paces, and then we can give them feedback to the coaches to indicate how much training they need to catch up on during the winter time. And then in the spring, we might do some what we call checkups, where they're out running on trails, out running on the track, and we will come along and basically take blood from them as they go by and get their blood lactate ions in the middle of fixed pace runs, which is quite challenging. Got some more data. I think I'll skip through this actually, unless you have questions. But what we end up giving the athletes and the coaches is very detailed pacing information for both heart rate monitoring, as well as what paces they should run at in order to achieve either more aerobic power or more anaerobic power in their training, or what sustained pace they could actually keep and keep decent running economy. And so we give very detailed kind of training zones for them to use, and the coaches use this very, very heavily. Okay, so I don't know what my time is. I feel like I'm going a bit fast. Maybe there'll be time for questions, but I wanted to stop and just pause and think back quickly about the things we just talked about. And I'll talk about, actually the next slide first, and I'll come back to this. So what are the holes in some of the techniques that we were just talking about? We talk about motion capture. It requires cameras, requires markers to be placed on the skin. What are the limitations with this? First of all, I have to do it in a closed environment like this, kind of not much light. It's not very real world. It's very much an animation setting, which is fun and super cool, but it's really not a real world situation. When we take the blood lactate readings from the athletes while they're on the treadmill in the lab, we have to take a bit of blood from their finger, like if you were measuring a glucose reading with the diabetic screen. And this is pretty good, and it's pretty accurate, and it's only so painful for the fingers. After a while, the athletes get a little grouchy at us and call us vampires and other nasty things, which we're quite proud of, actually. But is there a way where we can get that data without poking holes in the skin? And I think the answer is yes. And recently, there's a group in the UK and a group in the Bay Area here in the US that are starting to develop these little patches. You can see down on the left, and this person with unreasonably fit abdomen. Like most people don't look like this. So just a reality check. This is not truly human form. This is some superhuman type. Okay. So you can have some sensor that reads from the sweat that comes off the skin, different ion levels in your body. And there's quite a bit of error in this system, but they're refining it into a point where potentially you can get glucose and lactate and other ion fluctuations during activities and then put that straight to your phone. When we test people in the lab, we have a mask on them. So it's like going to the dentist and you have your mouth pried open and you got stuff shoved into your mouth. And in this case, imagine that with a nose clip on, so you can only breathe through your mouth. And imagine that you're running at maximal effort. That's the fun we have in our lab. So, but that's not real world either. So if I go out for a run, I don't carry along all this stuff with me to measure my oxygen carrying capacity. So there are some groups that are coming up with, I don't know if you can see, it's a bit dark down in the bottom center, some groups that are coming up with portable metabolic assessment tools, where I still have the mask on, I still have the nose clip on, still at the dentist while riding my bike or running, but now it's something that's mobile. And so there's a lot of accuracy problems with this, so there's a huge area of improvement that's ready to be exploited here, or a challenge to be met. But no one has done it yet, so hopefully you guys can. That would be great. Some of the other things about if we measure in the lab and we put these markers on, it's very dark, it's very constrained, not real world. There are inertial measurement units that are coming out, it's just accelerometers and gyros, probably similar to what you're already using in the robots currently, but that are being packaged into very small, kind of unobtrusive things that you can wear. These are different than Fitbits. These are different than what's, well, somewhat similar to what's in your phone, but the way that the data is being interpreted is different, so that I can go out for a long run and get details about how my limb was swinging as I ran, how the impacts were being transmitted while I hit the ground and running, and then if I can put heart rate information in there as well, a little bit of lactate, a little bit of glucose reading in there as well, I can have a full profile of what I was doing out on the run. So this may seem a little bit, I don't know, iffy, but Fitbits and the accelerometers used to get motion assessments have been around for about 15, 20 years, and it's only just now that people are actually integrating them into a place where you can get interpretive value from it and battery life that makes it actually possible to use. So I think there's still a lot of area of improvement there that can be exploited as well. Okay, so go back to the previous slide now. I work at the University of Oregon, so I think you should all come to that school for your training. No, we don't have an engineering program. No, we don't have a robotics program. I've heard there is a school between here and Eugene that does. I can't remember what it's called, but it seems like they do pretty good work. We have a number of colleagues that we're great friends with at OSU who are really pushing the boundaries on robotics, we feel. And in their engineering program is in my opinion, kind of nationally ranked for sure, even if some of the rankings don't agree, but robotics is definitely ranked very high at OSU. It's a very new program. And what we'd like to encourage is more interaction between our programs. So we have the human aspect, the physiology aspect, and the anatomy, and they have the brilliance of the engineering. And together, I think we can solve a lot of problems. So what I'd encourage you to do is maybe hopscotch back and forth between the two programs. Okay. So you can go to OSU for your robotics, come to University of Oregon for your physiology, go back for PhD, whatever you need, and then eventually come back to work here, I suppose. Is that the goal? Okay. So at the University of Oregon, there's a number of undergraduate research opportunities. There's not too many high school interaction opportunities, although it's not unheard of. It's just you have to be a bit persuasive. And if you're coming to this talk here, it means you don't live in Eugene, probably. So it might be a bit far to drive for your high school engagement. But for undergraduate, there's summer opportunities to come and research there that are paid. And there's the Honors College, where students will become involved in research by freshman year. And there's also basically funds to take students to conferences that are regional as well as national. Some of the regional conferences you may be able to attend now if you're interested. This next spring in Eugene will be the Northwest Biomechanics Symposium, and this is biomechanics programs from all up and down the coast, basically from Northern California up to UBC, and then all the way to University of Idaho, Washington State, and so on. And it's a bunch of geek professors getting together with their geek students, talking about their latest research. It's very informal, and you would definitely be welcome to attend. The American College of Sports Medicine is where a lot of physiology is talked about, and that's being held in Bend this year for the Northwest chapter. In February, there's a bit of snow in that area, and there's a mountain nearby where people go skiing, so you may consider that to be a good vacation. Come to Bend and learn some science as well. So at that point, this is what I'll have for you today. There's a bunch of students involved in our work, both undergrad and graduate students, and some clinicians as well. And just like to thank you for your time and your attention, and definitely take any questions you have.
So looks like those technologies will be available to elite athletes right now. So how much time before you think they'll be available to
It's a very good question. So the question is, this technology is currently available to elite athletes and not necessarily to the everyday runner who wants to go out. Some of it is available. It's just that the interpretation of the data is not available as much. So some of these inertial sensors are available for people to have and to use for feedback in their runs. There's a group out of a Microsoft transfer called Sensoria that has instrumented socks that are coming out. And they are trying to provide a lot of very specific feedback, similar to what we would with our pressure sensors, for maybe, I don't know, $200 for a pair of socks, and transmitters, of course, and apps. But a lot of the gap that's currently there is that you can't just go to the store and buy your metabolic assessment device and take it with you for your run. You can't just go to the store and buy, maybe you can, $150,000 worth of cameras to set up in your lab to go running around it. So there's a huge gap between the research capacity and elite level assessments and everyday consumers. So I think it's scaling down quickly as far as the affordability of sensors and battery life, but often the interpretation value is missing right now.
Very good. What do you think is, in terms of collecting data from sort of the biophysics of the body, what do you think is the hardest sort of sensor or hardest measurement to take?
The question is the hardest measurement or hardest sensor to record from human body with biophysics side of things. That's a good one. I think the mechanics side is relatively easy because it's physics and it's not so messy. When we start talking about blood chemistry and how to get blood chemistry, that's why we take the pinprick. But even that in the little handheld analyzer has more error than we would like. We would like to be able to take a vial of blood and analyze it on the benchtop and have 1% error. It's more like 3 or 4% error of measurement, which we don't find acceptable. But if I put a patch on your skin and you become sweaty while you run, how much more error is there? And it's quite a lot. So I think that is the most difficult, is to get a sense of what's going on inside the body chemically by measurements on the outside. So maybe a Star Wars tricorder, or Star Trek tricorder, sorry for the Trek fans, where we can, and this is coming along, but accuracy is a huge problem, to be able to get a sense of what's going on inside the body from the outside. So maybe Intel has some solutions. Do you want to share? Maybe later? Okay. Other questions?
So can you speak about any examples of collaboration with the industry, or where some of the research from University of Oregon has fed into in industry devices, or maybe with Nike or?
Yeah. So the question is about where the University of Oregon and its basic science research, if I can interpret correctly, has influenced industry or has been in partnership with industry to affect some change. So the number one for sure is Nike. As many of you know, Nike originated basically from Eugene in the University of Oregon track thing that was Bill Bowerman and Phil Knight. We still have a lot of collaborative interactions with Nike, not as much as we would like, of course. They're a bit too big now, honestly. So we have friends that work there, and we say, can we talk with you about this cool idea we have? And they say, yes, but I need to get permission. And then 2 weeks later, a month later, we hear nothing, and whoops, sorry, it went by already. So, but some of the transfers that have occurred are in the sensor side. So Nike is developing, I don't think I'll divulge too much here, but they're developing sensors to be embedded in shoes as well as towards watches and other things to try to use what's going on with Fitbit and those other tracking devices, but with much more data fed into it to actually accurately predict what your metabolic output is. So that's some interaction we've had with Nike in the past 4 or 5 years. Other industry collaborations are in prosthetics and getting more on the other side of my life at the University of Oregon, which is getting smarter control of robotic assistive devices. So either exoskeletons or prosthetic replacement of amputated limbs. There's really good robotic control structures coming out of Vanderbilt, coming out of Chicago, coming out of MIT. But most of those people have no neuroscience background and no neurology training, but they're fantastic design engineers. So they can design something that works exactly how they make it to be working. But then they give it to the human, and the human walks on it funny because the human is adapting to it in a different way. So I think there's some great opportunity there. Being approached is its hard. Yeah.
Another question.
How many sports are based on their ideas being implemented?
How many sports will our ideas be implemented in? So track and field is our bread and butter at the University of Oregon. We love it there. Even those of us in our lab that don't run, we still love to work with the runners. But there's any sport that's going on can be improved in the training aspects based on this science. So we've had consults from baseball, which doesn't involve a lot of running, but it involves a lot of technique. And so we can advise about motor training and motor control. Basketball, football, these are things that are very short bursts of activity. So very different than a long run, but we can still advise about how do you train and not injure yourself and get the most out of your metabolic economy. So pretty much any sport.